everyone. Welcome back to Lesson 2. In Lesson 2, we're going to talk about radiation, absorption, and reradiation. Okay, so gas molecules absorb electromagnetic radiation. And that absorption, they're going to actually transform this energy, this radiant energy, this heat energy into kinetic energy. Kinetic energy, kinetic means movement. If you want to study kinesiology in college, then you're going to be studying movement. And that's what a lot of PE teachers and sports trainers study. They study the movement of people. This motions of the molecules becomes more energetic because we're going from heat energy and light energy to moving around energy. So eventually that molecule is going to re-emit that energy as radiation, but until it does, it is moving and grooving around. And there is different kinds of movement that those molecules do. There's 3 different kinds. They stretch it out. Feels good. Take a little stretch break right now. Feels great. Stretch it out. Get your hands up high and stretch. They bend. Just stand up. Let's bend. Let's stand up and let's try to touch our toes with our hands. So we stretched. We did one of the movements that molecules do. They bend. Touch your toes. Do that. Waiting for it. It's going to feel great. Just do it. And now, that's a bending. Now bring it up high. Bring those arms up high. Let's do a little yoga session here. Now I want you to twist. Twist. Bring those arms around. Look behind your shoulder. Look to the right. Hold that position. Breathe in. Breathe out. Now the next breathe in, twist to the left. And as you breathe out, go back to center. That little yoga practice right there, we stretched, we bent, and we twisted. We just went over the 3 different ways that the kinetic motion takes place in those energized molecules. Now, because different molecules have different sizes and shapes, they stretch, bend, and twist at different frequencies. It's similar to the way that bells of different sizes and shapes make different sound pitches and tones. I have a bell right over here. So different bells are going to have a different pitch because they're different sizes, they're made of different materials. And that's the same with molecules. So they're going to bend, twist, and stretch in different ways. So that's why different gases absorb and radiate radiation at different wavelengths. Now we can use this information, and knowing how they're going to bend and twist, we can actually learn about what we have in a sample. We can look at gases, and we can figure out how is this gas being twisted and bent and stretched because of the amount of energy that it absorbed. And that's called an IR spectrum or infrared spectrum. And when I was in college, I had different liquids and powders of chemicals. I didn't know what they were, but I could actually put a bunch of energy into them, into this special machine called an infrared spectrometer. And looking at the printout of the graph, I was able to figure out, do I have, something that has oxygen in it or nitrogen in it? Do I have an alcohol group, looking at different organic molecules? So this is a way of figuring out what you have in the atmosphere and the quantity. Okay, so we're going to look at the oscillations, the movements of water molecules. So how do individual atoms vibrate within the water molecule structure? So water vibration modes. Molecules vibrate at frequencies that depend on their mass, their size, and the types of vibrations allowed by their structure. The different kinds of vibrations can occur all at the same time. So you can stretch and bend over at the same time. Like when you touch your toes with your arms, you're not just bending, you're also stretching. You can even twist. You can reach over, touch your toes, and then walk those arms over to the left, and then walk them over to the right for a bending, twisting, stretching experience, which might feel great if you do. You can do that. So it's not just one or the other. They can be one or the other, or it can be a combination of a twist and a stretch, or a bend and a twist, or a stretch twist situation. So it can be all of them. The distances between the atoms of water molecules can stretch in and out like a spring. This can occur symmetrically with both hydrogen atoms going in and out together, or asymmetrically. So let's look at a picture here. Okay, so we can have symmetrical stretching, where if you put your arms up and your arms are out together like you're in cheerleading, you're doing a high V, making a V with your arms are stretching and it's symmetrical. You can also like move those shoulders, and you can get some asymmetrical stretching going on there if you get some shoulder movement in there. And you're getting asymmetrical stretching where one arm is being stretched to the right or left more so than the other. We can also have bending, which bending can be kind of like wagging. It's kind of another kind of thing. So we have stretching, bending, and twisting. So we can have in plane and out of plane bending. So put those arms in a high V. We can do some scissoring, which is a type of bending where we're going in. So if you bring those fists together in your high V, that's scissoring. You can have a rock where you're like going side to side. And you can have wagging where your arms are going up and down. You're waving your arms. Hey! So twisting is when your arms are going to go forward and backward. You're going forward and backward like you're, drumming, like a really big drum or something. So that would be a twist, is where they're going kind of forward and backward instead of just side to side. So a stretch, we're going up and out, and it can be symmetrical or asymmetrical. Scissoring, we're going towards or away from each other, kind of on a horizontal plane. And then the twisting is going to happen more in a vertical plane. So think about like our X, Y, and Z. Okay, but not just water that does this, it's other molecules too. So water. So why do we care about water oscillating and stretching and bending? So water and water vapor. The most powerful greenhouse gas is water vapor. That's kind of unexpected, right? So, and to even think that water vapor is even a greenhouse gas, we didn't even look at it in our greenhouse gas chart in lesson 1. So you're asking me like, what the heck? So water vapor accounts for about 50% of the total absorption of infrared radiation in the atmosphere. Clouds are there, they're in the atmosphere. Clouds contain liquid and solid water, and they count for another 20%. And carbon dioxide, methane, and everything else absorb the remaining 30%. So the most abundant greenhouse gas is water. However, water vapor also absorbs some wavelengths of incoming sunlight, so it's both warming and cooling effects. So it's kind of interesting. So water vapor in the atmosphere is impacted indirectly, not directly, by human activities. Oxygen and ozone. Ozone is O3. So it's kind of like oxygen gas, except another oxygen. It was like, hey, can I hang out with you guys? And it was like, okay. So it's a gas and it's O3. It's a power absorber of the sun's ultraviolet radiation. Ultraviolet radiation is dangerous to living tissues. It is a mutagen. So UV light can damage your DNA and cause it to mutate, which can cause things like skin cancer. So that's why we can use sunscreen to help block or reflect that ultraviolet light from absorbing into your skin cells. So ozone absorbs ultraviolet radiation so it doesn't enter your skin. So it's like a protective layer around the earth. And that's why it was very important in the 90s where we had these holes in the ozone layer, because in the 80s, everyone was using hairspray with those CFCs, and they were literally causing holes in the ozone layer because their aquanet was like destroying the planet. So the ozone layer in the stratosphere is very important, and international action was taken to stop the release of chlorofluorocarbons when it was discovered that those gases were destroying the stratospheric ozone. And today, it's pretty much healed up, which is amazing. It just shows you that humans can change things for the better. It's not all bad. We can help the climate. We can help the air and the water and all those things. And if we look at what's happening right now with pollution, where everyone's staying home and not driving their cars, we see really good air quality. We see clear water. And so these things can be changed and helped. It's not all bad. Okay, so let's look at carbon dioxide and methane, and let's look at their bending, stretching, and twisting. So in general, a molecule will have more absorption nodes if it has more atoms and if the molecule is asymmetrical. So let's think about oxygen gas. Oxygen gas is not very big. It only contains 2 oxygen atoms. It contains a double bond, and it's a symmetrical molecule. So oxygen gas has fewer absorption modes than water. Water contains hydrogen and oxygen. It's a polar molecule. So it's going to have more absorption modes. Carbon dioxide actually has fewer modes than water because carbon dioxide, although it's a little bit bigger of a molecule, it's symmetrical because the carbon and the oxygen, they both have a double bond, but it's equal on both sides, so it's symmetrical. So water is going to be better at absorbing than carbon dioxide or oxygen gas. So we can also think about isotopes. We talked about isotopes last week. If you recall, an isotope has the same number of protons, but a different number of neutrons. So we have some common carbon dioxide molecules, and they can have a different number of neutrons. So we have carbon 12 and carbon 13, and those carbons can combine with different kinds of oxygen. We have oxygen 16, oxygen 17, or oxygen 18. So each of these possible combinations will have different mass distributions, and they will all absorb radiation at different wavelengths. So not all carbon dioxide is created the same because some of it will contain different isotopes than another. So some will be better and some will not be as good at absorbing that infrared radiation. So let's look at some bending and twisting. Let's look at oscillation. So oscillation is movement. Okay, So let's first look at carbon dioxide. So I like this little picture here because it's showing us in a very clear way of what bending, stretching, and twisting can look like for carbon dioxide. So carbon dioxide actually is really just going to stretch and bend. So if you put your arms out, you can be carbon dioxide, and if you have your arms go up and down like you're waving, that's bending. Now, because of that double bond, it can't twist. It's sad, it just can't twist and shout. It can only bend and stretch. So it can stretch by going side to side, side to side. So if you get your arms out really wide and one arm is stretching over and the other arm stretching over, all these oscillations feel really nice. You guys should oscillate at least once a day. It's great for your back. It's good for your heart. Oscillate, also known as do some yoga. Now let's look at some methane. So methane is CH4. So whatever's happening on top is also going to happen on the bottom. Now remember, we can have these oscillations going on at the same time. So we can have symmetrical and asymmetrical stretching, right? So if we're looking at symmetrical stretching, we're just kind of going like up and down or in and out, and it's symmetrical. Or we can be asymmetrical. We have something called scissoring. So it's kind of wagging in and out. Now think about that happening at all different parts. There's 4 parts, right? So if your hands, you also have to wag your feet. So it's kind of like making a snow angel. If you've ever made a snow angel, you lay on your back and you wag your arms, you wave them around and you wave your feet. So that's kind of what scissoring is like. It's happening in one plane. Now we can also do wagging where your hands are going back and forth, but your feet also have to go back and forth too. So this would be like, you'd have to like be on your bed or something and you're kind of flailing about, going back and forth. You can twist your arms and twist your legs, and then you can rock back and forth and shake your hips, shake your arms and shake your hips. Okay, so if you combine all those different things, you can get lots of different movement. It's kind of like the twerking of the methane molecule. Okay, the last thing we're going to talk about in this lesson is incoming and outgoing radiation. So incoming radiation, that's going to happen from the sun. About 55% of incoming solar radiation passes through Earth's atmosphere and reaches the surface. So most of that light energy, that electromagnetic radiation, 55% of it is going to reach the surface. Of the sun's energy that reaches the surface, about 12% of it just gets reflected right back out into space. Okay, so of that 55, 12% of it is just going to shoot it right back out into space. The rest of it is going to be absorbed by the surface. Of the 45%, if we're following this, that doesn't reach the surface, so 55 plus 45, we're going to get 100, right? So 45, the part that didn't reach the surface, about half gets reflected back out to space by Earth's atmosphere. Thank you, ozone layer. Thank you for people stop using Aquanet in the 90s. So that's going to get reflected back out by Earth's atmosphere, and half of it is going to actually be absorbed by the atmosphere. So it's not going to reach the surface. It's going to be absorbed by the atmosphere. So half of that 45 goes out into space and half of it is absorbed by the atmosphere. The absorbed radiation is largely ultraviolet, and it's absorbed by oxygen and ozone molecules and short wavelength infrared radiation. So that ozone layer really protects us from that damaging and harmful UV light. UV is also what tans your skin. So ultraviolet radiation, it affects the melanin, the pigmentation that is in your skin cells and causes it to darken. Okay, now we're going to look at outgoing radiation. Outgoing radiation. Earth's surface warms as it absorbs that incoming sunlight, right? That's why in the daytime it's hotter than in the nighttime. Because in the daytime, the Earth's surface is facing the sun and it's absorbing that sunlight. And it re-radiates, so it's going to go back out into space or just out roughly the same amount of energy it receives. But this time it's a long wavelength infrared spectrum, so it's heat. And the background of this image is long form radiation. The infrared radiation is absorbed by greenhouse gases at those very specific wavelengths corresponding to the different modes of molecular oscillation. So the outgoing radiation is going out into the atmosphere and it's causing those molecules to be energized, causing them to wake up and do some stretching and some bending and some twisting at very specific wavelengths. Only about 10% of Earth's outgoing infrared radiation passes directly out into space. So most of it is going into the atmosphere for those greenhouse gases to get excited. So the 10% that goes out, we call it the atmospheric window, such as the notch seen in the total absorption curve at wavelengths around 10 micrometers. About half of the radiation absorbed and re-emitted by greenhouse gases goes back to Earth's surface. So that infrared radiation excites those molecules in the atmosphere, and those excited molecules, they twist and they bend and they stretch. And once they're done with that kind of dancing around, they're getting hot from that movement, so they let it go. And what they're letting go is some more infrared radiation, heat, and that's heat in the Earth. So the energy warms Earth's surface and is re-irradiated again. So it just goes over and over in a loop of it's hitting the surface of the Earth, and the Earth's surface is throwing it back and saying getting hot. And then it's exciting those molecules and making them dance. And then they get hot and they're like, I'm hot, I'm sweaty, get rid of this radiation. It goes back to the Earth. So if the amount of greenhouse gases increases, the amount of energy stuck in this loop increases, and the loop just keeps going on and on and on. And that is lesson 2. In lesson 2, we covered the oscillation of different molecules, and we talked about radiation, absorption, and re-radiation. So thank you for listening to these 2 lessons this week. I hope you enjoy the other activities, and I'm looking forward to seeing you or hearing from you in our Zoom meetings. Thanks.